So we've talked about work and kinetic energy, and now we're going to talk a little bit more about how they're connected. But first, just a reminder about what work is. It is the integral of a force dotted over the path of the displacement. And, if you take a look at that and remember what we know about integrals, I will also tell you that work is the area under a force versus displacement curve. So force does this, work is going to be, if you go from there to there, and that's your displacement, work is going to be this area under the curve, just by virtue of kind of how you can interpret an integral. But that's what work is for an individual force. Now we need to talk about net work, and that is just the sum of all the different works on a particular object. So if, for example, you've got some little block here and it has a force, we'll call it force 1, pointed that way, and another force pointed that way, and another force pointed that way, and a fourth force pointed that way. So forces all over the place. In each of these forces, we could plug into this work equation and look at its displacement, how it compares to the displacement, how this little block is traveling. And then we get the net work on this object by adding up each of the works done by these four different forces. So the net work is the sum of all work done on an object. So the nice thing here, though, is that work's not a vector. The dot product or scalar product produces scalars here, so we don't have to divide work up into components. Yay, that's nice. So we get the net work. So for example, let's go ahead and think about how we might calculate this here for this particular case. That means we'll need to know what the displacement is. So say this little block starts here and travels this way, and that's its displacement from here to there. Then in this example, we'll say all forces are constant. And if we have the forces are constant and the displacement's in a straight line, then this integral is nice and easy to do. So here the work for each of those forces is going to be the force dotted with the displacement vector. So let's go through and figure out which each of them are. All right, work 1, that is going to be force 1 dotted with the displacement vector, and force 1 is headed off in that direction and the displacement vector is headed off in that direction. And remembering what we learned about the dot product, that is equal to the magnitude of the two vectors, so the magnitude of force 1 and the magnitude of the displacement, or the length of how it's been placed, and the cosine of the angle in between them. So here, the cosine of this angle, force 1 is pointed that way, the displacement is that way, this cosine is 180 degrees. And the cosine of 180 degrees is -1. So this work is negative the force magnitude times the displacement length, and that's the work done by this force. Now force 2, you do something similar. We'll do the force 2 vector dotted with the displacement, but here, go here and say, all right, force 2 magnitude, displacement, cosine of the angle between them. We'll call that theta 2. Well, force 2 is this way, and the displacement's that way, so this angle is 90, but cosine of 90 degrees is 0. So there's no work done by force 2, because that force is completely perpendicular to the displacement. And the same thing will be true of force 4. Here, the force and the displacement vector are also perpendicular, so we can also say that the work done by the fourth force is equal to 0. So that leaves just this third force. So what is the work done by that third force? Well, it is force 3 dotted with the displacement vector. So their magnitudes times the cosine of the angle between them, but the cosine of the angle between them is the cosine of 0 because they are both pointed in the same direction. And the cosine of 0 is just 1. So this is just going to be the magnitude of force 3 times the displacement. So if we want to know what's the net force for this particular example, where we said all the forces are constant and this is displacement, well, now we can write in specific values, or at least equations for these guys. So the work done by force 1, it's negative the magnitude of force 1 times the displacement. The work done by force 2, because the force and the displacement are perpendicular, it's 0. The work done by force 3, well, those two are parallel, so it's just the magnitude of force 3 times the displacement, because we are dealing with nice constant forces and straight line paths here. And the work done by force 4, well, that one is also a force which is perpendicular to displacement, so that guy is 0. So in this case, for this particular situation, the net force, I can just go ahead and clean this up here, and write it a little bit bigger, would be negative force 1 times the displacement plus the magnitude of force 3 times the displacement. And we can sort of say that sort of makes sense. Force 3 is in the direction of displacement, so that should do positive work. Force 1 is in the opposite direction of the displacement, so it would do negative work. And forces 2 and 4 are perpendicular, so they don't do any work at all in this situation. Well, why do we care about net work? Let me kind of erase my example here so I have a little more room. The reason we care about net work is the work energy theorem tells us that the net work done on an object is equal to the change in energy of that object, or, the final energy after all the work is done minus the initial energy before any of the work is done. And the only energy we know about right now is kinetic energy. So we can be a little more explicit here and say this is 1/2 the mass times the final velocity squared. That's the final kinetic energy, minus 1/2 times the mass times the initial velocity squared. That is the initial kinetic energy. And that is equal to the work. And the work is, of course, equal to the sum of all of these integrals for all the different forces dotted with their displacement. And you will notice, so this is a sum of a whole bunch of integrals to get all the different works to get the net force. And this is a subtraction of two things which are not integrals. So if we have the information of what's going on in energy, this side is a lot easier to solve for. But at a more fundamental level, let's look at what this equation is telling us. I talked a little bit of how work is really how objects interchange energy in between each other. So if an object was having positive work done on it, that would mean that a force was giving it energy. And if the work done on that object was negative, that means that force associated with that negative work was taking energy away. And that's really what the work energy theorem is telling us. We're looking at all of the objects' energies that are sort of flowing in from the outside. Some energies are coming in, some energies are going out. So positive works are energies flowing in, negative works are energies flowing out. And the total of all of that energy flow in and out is going to be, of course, the difference in how much energy the object has at the end versus what it has in the beginning. So energy the object is receiving or losing is equal to the change in energy. And one more thing, one more concept to think about here is whenever we have sort of changes in energy, we often are interested in how fast that change is happening. That's also true in work. So the change in this energy flow, the rate at which that change is happening, that is known as the power. So power, we use P to symbolize that. It is the derivative of work with respect to time. If you're lucky enough to have things in a simple world where these works are done by constant forces, and we could put in, it's just the force dotted with the full displacement. And if again your force is constant, well, you take the derivative of a constant, that'll just come out, and you'll have force dotted with the displacement over time, and a change in displacement over time. Well, that's the velocity. So power, if, and this is a big if F is constant, then you could say power is equal to the force dotted with the velocity. So these are the big conceptual things that might be useful. Let's see how this actually applies in an example problem.